All right, so I've already said this before, my name's Daniel, and today I'm going to be talking about vehicle security. I aim to kind of cover a lot of different topics, so more breadth rather than depth in this talk, but we will be touching on a lot of different things and then really going in detail on the CAN bus, which we will discuss what that is and get into. But first I want to start out with a video. Hopefully the audio works. To give you some context, it's a car research company and they're dealing with key fobs, so like keyless entry. Let's see if, okay, let me get audio working here real quick.
Are they like keyless entries that just like even if you push unlock and the car unlocks? It's like a button?
Well, okay, so I should, I guess.
Or is it like where you have the key with you and you push the button and the car starts, like the ignition goes?
Right, so it's actually neither of those. This is the keyless entry system on the newer cars where if I walk up to the car and I'm within an appropriate distance, the car will unlock. Or if I'm inside the car and I press push to start, if the key fob is recognized as being close enough to be in the car, then the car will start. So yeah, and they'll explain that here.
With a keyless entry system, this is how it works. One person extends the range of the key fob left somewhere in the house. The thief's accomplice can then open and start the car within a matter of seconds. When you have a car with a keyless entry system, you just carry your key fob in your pocket. Once you're within 2 to 3 meters of the car, it will recognize the key fob, unlock upon touching the door handle, and start when the driver sits in the car. To steal this kind of car, all you need is to extend the range of the key fob from a few meters to several hundred meters. The car thinks that the key is quite near. All you need to do is start, and within seconds, drive off without leaving any visible traces. IASG wants to find out, are keyless entry systems really that easy to trick? The unsuspecting victims are sitting in a cafe with the key fob on the table. Now, all the fraudster has to do is sit nearby with a simple range extender. The second thief, waiting outside, opens the car door unnoticed and drives off. This theft method worked well in the IASG test. The thief can drive the stolen car until it runs out of fuel, or if he simply leaves the engine on while refueling, he can virtually drive forever. In other words, taking the stolen car out of the country is no problem.
So the basic premise of this, as they'll go on to explain, is they do their own tests with a bunch of different cars, and not only does getting into the car, but also starting it work for every single test they did in every single car. I don't know the exact range of different manufacturers and models that they had, but it was in the teens or above of what they've tested, and they're continually, as a research firm, testing more and more cars and finding that they're susceptible to this. So this kind of gets you thinking about what problems there are with cars, and there is a reason that this problem can't easily be fixed other than get rid of the feature, and that is mostly because of safety. So if you have a key fob that can start the car, but you want to solve the problem of being able to steal it, well then you could just shut down the engine and then the thief can't get away. However, that's a safety issue because what if the normal user leaves their key fob or it falls out the window or something, and then their car shuts off on them. So basically they go on to talk about how there really is no good solution for this except for getting rid of that feature, and they call on the car manufacturers to work on something to remedy this problem. So this basically just scratches on the surface of the security implications that we're dealing with cars. So, okay, so I want to give a quick overview of what I'm going to be talking about today. So we're going to start with how this talk came to be and why you should care about vehicle security. We'll go into talking about threat modeling a car and how we can look at the different attack surfaces with different types of vehicles. We're going to be talking about the CAN bus, or controller area network, and that's the primary network of modern day cars. We'll talk about reverse engineering the CAN bus, both virtually and on an actual vehicle. Okay, yeah, real car CAN testing. And then we'll talk about keyless entry PIN codes on the actual door of cars and how we can brute force those in under 20 minutes. We'll talk about a thing called TPMS, that stands for Tire Pressure Monitoring System or Sensor, and the implications behind those. And then we'll touch very briefly on infotainment systems. And finally, I've got a bunch of resources that you guys can look at and links to those for after the talk if you guys want to go through these slides. So why do I want to talk about vehicle security? I originally got started with this by seeing the DEF CON talks by Charlie Miller and Chris Balasek, I think is how you say his last name. And if you guys aren't recognizing the names, you may have heard of them as the Jeep hackers. These guys basically tore apart, I believe it was a Jeep Cherokee, and they've done this over years and years of research. But long story short, they were able to remotely control a Jeep and to the point of shutting off the engine and basically taking full remote control over the internet. And they were able to enumerate other vehicles that were vulnerable to this issue, and it was in the many thousands. So this was a huge issue, but I believe Jeep has since fixed it. This talk kind of came to be because of the independent study course. If you guys have not heard of this, I definitely recommend looking at it to take as an elective. It can count for up to 2 credits if you take it in 1 semester, or you can do 1 credit and 2 semesters of it. But you basically get to study whatever you want. So if you must be a senior, so if you are or you're going to be a senior, you should definitely look at doing this because you can kind of study whatever you want as long as you get an instructor to approve the topic. So, okay, I wanted to go into vehicle security and kind of learn about it because I know the vast majority of people I know operate vehicles, and therefore the attack surface and possibilities are high for malicious actors. As you've seen probably as you get into different cars and through the news, they're becoming more connected and networked and reliant on different technologies like autonomy, and also being able to connect to our phone and interact over wide area networks. So I wanted to know, the whole goal of this entire research was what kind of damage could a malicious actor do to newer modern cars with said technology. Okay, so now why you should care about the security of cars. These are 4 snippets of different things in the news. First one, I believe these 2 are both referring to the Jeep hackers. But flaws in vehicles allowing you to disable safety features, taking control of steering and braking. This was done remotely. And then also, this was Elon Musk and Tesla and the Boring Company working on autonomous vehicles. So the security implications there of a malicious actor getting in and taking control of hardware that can turn the car and accelerate the car is a safety and security issue. And then finally, this was a screenshot I took on an actual car manufacturer's website where they are really pushing the smartphone connectivity to the car. So really having technologies interact with your vehicle is all increasing the attack surface for somebody to do something potentially bad. Okay, so now I want to talk about threat modeling. So the goal of threat modeling is to identify any sort of vulnerabilities that may be within a given system, and the system we're looking at today is a modern car. So we want to think about the level of system access that we have, and the 2 of those for a car are likely going to be whether you're outside of the car and it's potentially somebody else's car, or whether you have internal access and you're sitting inside, and we'll talk about things like the OBD2 diagnostics port, USB ports, and all that. So can anyone give me an example of a potential technology in a car that might be an interesting attack surface for a hacker? Does anyone have any ideas of like any sort of technologies? Yes?
OnStar.
OnStar, yes, so that's absolutely right. OnStar, I believe, works over satellite, Arden? Yeah? Okay, so satellite communications, remote communications. Do you know what kind of stuff OnStar can do or is capable of doing?
I believe it's able to call out in case of emergency. Mm-hmm. And that's the main feature that I know of. I believe it also might have something to do with being able to report its GPS location over that.
Okay, yeah, so.
Direct told me to start cars.
Okay, yeah, so I believe on some vehicles that is a thing. I saw a hand back there. Anyone? Or no? Yeah, go ahead.
It can unlock your vehicle.
Right.
If you lock your keys.
Yeah. So yeah, Onshare's one.
So in addition to all that positive stuff, you can also shut down a vehicle. You can throttle the engine down to like 800 RPM so they can just barely move.
Oh.
It's not just happy.
Right. Yeah. So, okay, so OnStar, anybody have any other ideas of technologies in a vehicle that an actor may target? Yeah.
I know there's been a hack where they use the FM radio station to attack the infotainment system and then jump to the car.
Okay. Yeah, absolutely. I haven't heard the FM specific one, but that's definitely
I
interesting.
think that's part of the Jeep one.
Okay. Yeah, go ahead.
I think also part of GPAC was the self-parking systems help park.
Yeah.
Flip tax for there.
Yeah, that's an excellent point. So when you have cars that, we'll talk about this a little bit more, but when you have cars that have park assist enabled and other features that are relevant to that, they come with hardware that can control the steering and acceleration of the vehicle, whereas on older cars, something to move the actual steering wheel electronically isn't enabled, but with park assist, you need that technology. So henceforth it's in there and somebody could target that to control the car. So that's all great. Cool. So I've kind of developed this diagram with a crappy cartoon car, just highlighting some of the just some of the components that an attacker may target. We kind of talked about the wireless technologies. Some cars have Wi-Fi access points and also allowing you to hook up your phone with Bluetooth. So Bluetooth's there. We'll talk about keypad entry and brute forcing that. And then we touched on the infotainment or navigation systems, so the center console showing the maps and stuff. The OBD2 diagnostics port we'll get into in just a second, and then TPMS, and also the ECU or engine control unit is basically a chip that is managing, and I don't know cars all that well, but basically managing how the engine works from a performance and also a fuel saving perspective. So that's tuned by the manufacturer, and also some people do it aftermarket as well as a hobby or if they're really into cars. So, all right, so now we're gonna get into the CAN bus or controller area network. As I said before, it's the primary network on a vehicle. There are other networks. In fact, I believe it's Tesla cars that even have Ethernet, and that is more for kind of the infotainment and entertainment purposes of a vehicle, whereas CAN bus is more of a fault-tolerant, very high-speed network. So just get pulled up here. Okay, so the CAN bus is a network of nodes, and each of these nodes have three components. First component is a transceiver. You can kind of follow along in this diagram here. And so that basically converts the voltage levels on the CAN bus to the levels that the CAN controller, which is tied to a node, can read and then use, and then also vice versa when we're transmitting onto the CAN bus. So then we have the CAN controller, which is tied into like the node's microcontroller or processor, and that is mimicking the, or representing the link layer in the 7 layers of the OSI networking model. And then finally, we have the processor or the microcontroller that deals with or is controlling said node. So CAN was made mandatory for all vehicles in 2008, and that's why it's a good thing to learn if you're interested in getting into car security or car hacking, and you'll find it on pretty much all consumer vehicles nowadays. So like I said before, the goal of the CAN bus is to have quick and bursty and short frames being sent across the wire so that you have fast communication. It's also extremely fault tolerant, and we'll discuss the techniques that the CAN bus uses to implement that. And so long story short, it's pretty hard to mess up something on the CAN bus in terms of breaking the CAN bus, as it was designed to be like that. The nice thing about CAN is it's a very simple protocol, and there's abstractions built on top of it that allow you to do more things with it that we'll look at. But CAN by itself is a simple protocol and with small frames. Oh, and also an example of a transceiver in the real world is the MCP 2551, and I included a link to that if you want to look at the data sheet and like for that. There are the OBD2 like wireless plugins that you can use on cars, and some of those use the 2551. So, Okay, so this is a diagram I made to kind of demonstrate the CAN bus. So we've got 3 nodes here. There's a lot more nodes in a real car, but essentially you've got 2 lines of twisted pair wire that are terminated by 120 ohm resistors on each end. And so you've got 2 wires, one being CAN high, one being CAN low, and they're both, the nodes are transmitting voltage signals onto the CAN bus, and everybody that's on the CAN bus can read whatever's on there. So that from a hacking perspective is great because we can see all the traffic. Okay, so the way this works is the CAN high is transmitting what the CAN low is, just the inverse of it. And so I want to ask a question to the audience. Why do you guys think there's the same signal, but it's the inverse? Or essentially, CAN high is transmitting at the same level, and CAN low is transmitting at a negative level just below that, but they are essentially representing the same thing. So why do you guys think that why do you think it's set up like that? Why did the designers implement it that way? Yeah.
Noise?
That's right, yes. So, yeah, so we'll talk about it in the next slide, but there's something called differential signaling that is saying if I pick up something on CAN high, I'm going to compare it to CAN low. I'm going to compare that inverse. If it's not exactly the same, I'm going to drop that as noise. And that makes the system more fault tolerant and ignoring any sort of noise that may be introduced on this network. So yeah, good answer. So next question I have, if our transceiver here, or sorry, the controller was the data link layer, then what is are the wires here? What OSI layer would that be? Does anybody know? There are 7 here. So we got physical, data link, network, transport, session, presentation, application layer. Does anybody have an idea or a guess as to what layer the wires would be? Yeah, go ahead.
Would it be the physical layer because of the copper wires?
Yep, exactly. So good answer. I don't know if I say here. No, I don't. Okay, but yeah, you're right. So it is a physical layer. It's essentially the wires are defining the data, what's being used to transfer the data. So, all right, good answer. And again, that's just voltage levels. Okay, so now we're going to talk about the frame, or essentially just one CAN packet that you might find on the wire. Again, it's pretty simple. There's not much going on here, you know, compared to some other frames you might deal with other protocols. Again, differential signaling, as Walker said, will cancel out noise because it's going to basically act as an error check. Another thing, the CRC, which if any of you have taken networking classes or have looked at networking protocols, is pretty prevalent in other protocols. CRC stands for cyclic redundancy check, which basically makes sure that no bits were flipped or there was any error introduced as it was being transmitted. There's a lot of math behind it, and I'm not going to go into that. But essentially, it makes it more fault tolerant. So, okay, I'm going to try to skim through this and not take too much time on it, but essentially the important parts of the CAN frame are your 11 bits of your arbitration ID. The arbitration ID defines essentially what the packet, or the frame is responsible for. And so we'll see that as we reverse engineer later on in the talk. I'll skip RTR here. Another important one is the data length, and so that's essentially just how many bytes of data we're dealing with. On a standard CAN frame, it's always going to be one byte or just 8 bits of data. So as you can start thinking about this, that's really not a lot, and there's not a lot you can represent with just 8 bits of data. But again, it's supposed to be short and bursty for real-time operations on the actual bus. And then, yeah, so you have your 8 bits of data. You can see here kind of like voltage levels and the difference between CAN high and CAN low, how they're inverse of each other. And as you get the higher voltage levels, or excuse me, the lower voltage levels will represent a 1, and the higher voltage levels for CAN high represent like a 0. So then your drop off represents the changing of what the digital bit is representing. So any questions about the CAN data frame because this will play a crucial role as we start reverse engineering CAN. Okay, not seeing any. One thing I do want to touch on, the transport layer of CAN, or an abstraction of transport layer on top of CAN. It's called ISO-TP. Yes, so we've seen that a typical CAN frame will only transmit 1 byte or 8 bits of data. That's not a lot, and we may have purposes that we want to send more information in a single frame, or sorry, not a single frame, but in a single message onto the CAN bus. And we can use ISO-TP to do that and extend that range to 4,000, up to 4,095 bytes versus just 1, which is pretty great. This is most commonly used. Has anyone ever used the OBD2 like to read error codes on a car? Yeah. So ISO-TP is used because the diagnostic messages, you want to send more information about what's going wrong with the car, and so it'll typically the cars will use ISO-TP to send that information to the OBD2 port, which uses the OBD2 protocol, and henceforth the need for longer message sizes. There's a cool part of the CAN use utility, which we'll talk about later on, but there's a utility called ISO-TP-TON, which lets you use the internet protocol between 2 nodes over CAN, which I think is pretty cool. Yeah, and then ISO-TP used whenever large amounts of data. And then a caveat of this is if we send a lot of information over the bus at one time, we may flood it, which may require a restart of our car. But again, it's pretty hard to break the actual CAN bus. So myth or fact, the barrier to entry for CAN hacking is high. Who thinks that it is? Okay, one person. And why do you think that?
There's not a lot of documentation.
Okay, yeah. So in terms of a car hacking perspective, you're right. A lot of the arbitration IDs are proprietary. Like the manufacturers don't just give out what CAN frame does what, and we'll talk about why that and why we have to reverse engineer and why that takes time. So you're absolutely right. Another thing that I personally thought when I started this is well, I need a vehicle to do this. I need hardware to do this. But I want to kind of dispel that and say that it is a myth, and we don't even need a car to begin playing with CAN. So there are many options you can go to do this. I'll show a book at the end, but it basically describes how you can build a physical test bench by going to a junkyard and pulling out hardware from cars and then just putting together a test bench. Or you can either go easier than that and do all this from the comfort of your laptop with something called IC-SIM, which if any of you were at Nationals, there was an anomaly for that. And there may be some at ISU too, who knows?
Dun, dun, dun.
Yeah. Okay, so before we can start playing with CAN, we need to know a little bit about Linux and CAN utils and understanding what Socket CAN is. So Socket CAN is developed by Volkswagen, and it is open source, but it's essentially CAN drivers for Linux, for the Linux kernel, and the networking stack to deal with basically CAN network interfaces. So allowing us to sniff and treat it as a normal network interface. And so that is a thing. And then also there is CAN utils, which is a repository of utilities that have been created that allow you to do numerous things with the CAN network interfaces, such as dumping all the CAN frames as they are coming over the wire, putting CAN frames or writing to the CAN bus, and also different utilities that help us reverse engineer what's going on. Okay, so I talked about IC-SIM really quickly. This is essentially a car simulator for CAN that you could run on your laptop. Prereq is Socket CAN and CAN utils, which we've just talked about. And what it does is it uses a virtual CAN device. So this is basically a CAN device, but it's done virtually and set up on your computer without any external hardware needed. And you get a instrument GUI, which we'll look at in just a second, and also a control GUI to send inputs to your car. So then we, as researchers, can use this simulator to help us understand the process of reverse engineering the CAN frames and understanding what's going on in a car. So now I'm going to demo that, and I'm not going to do a video because that's not fun. That was, I guess, more of a fail-safe, but we'll switch over here to a single display. Oh, no, that's not what I wanted to do. I will do a mirror. Cool. All right, so let me just pull open a terminal here. Hopefully that's big enough. One more. Yeah. All right. So I've got ICSIM and CAN utils already installed, including socket CAN. So those are the prereqs for that. But anyway, once you get the ICSIM repository downloaded, there's a nice little script here that just sets up your virtual CAN device. And so all you have to do is run that to get that going. It's very simple. So we'll do that. And then, okay. And then if we do, if we run IP and list all the network interfaces, we can see our virtual CAN device is now created. And we can start interfacing with that. So first thing we're going to do is we're going to start up our simulator, our instrument cluster on the virtual CAN device. And so we get this little guy. So you can see we've got a car. It'll turn red when the doors are unlocked. We've got a speedometer here, and then we've got a left turn signal and a right turn signal. Pretty simple, but it gets us started here. And then, actually, let me do this. We will get the control started on VCAN 0 as well. I don't know why they chose to do a PlayStation controller for inputting controls, but they did. So that's, we'll put that there, and then we'll drag over the actual instrument cluster. So now it's saying, if I want to do my turn signals, I do left and right arrow, and you can see them come on. So left, right turn signal. If I go up, you can see the speedometer start to increase and accelerate as the car takes off. And then I can also unlock doors by holding down right shift and selecting A, B, and other ones. So that's what that looks like, but we're not actually seeing any of the CAN frames because we're not dumping any of them yet, which we can do now. I will open up another terminal, and let's head into CAN utils. So there's a lot of different utilities here, and they're not greatly documented, so you kind of have to go through and read some of the code for them in the comments to understand what they do. But we can do CAN dump, so let's just run CAN dump real quick, and this will dump out all the CAN frames on your network device. So we actually have to specify the network device, which is VCAN 0. And now you can see right here, all this is, mostly in the hex here, you've got your 11 bits for your arbitration ID, and this is the actual data that's associated. We talked about how this is 8 bits or 1 byte of data that's going across the network. So that's great, but it doesn't really tell us anything. We're just looking at a bunch of numbers. So this was, not exciting to see at first. However, there's also another utility called CAN Sniffer. What CAN Sniffer does is it basically only shows what fields are changing. A lot of frames will be repeated, or a bunch will be sent, and not all of them are changing. So it's going to filter out, and then we can also apply further filters if we want to look at a range of arbitration IDs, or if we want to look at a specific arbitration IDs. So we can do a bunch of filtering to get only the frames that we want to actually look at. So I'm going to add the -C flag. That's going to colorize the changes and make them red, so we see them even in a nicer format. And then we'll just run it on our VCAN, our virtual CAN device. So I'm going to zoom out here real quick. And then we'll pull up our instrument cluster, and we're going to do a real simple test here. Now, I will say this is a lot less than you'd see on a normal car, but for the purposes of testing and understanding how this works, it's nice. But if I start using my left and right turn signals, so who can see the arbitration ID, or thinks they can, as I switch from left to right?
40C.
Not 40C. I'm trying to find that one. Where is it?
Here at the bottom, 4th from the bottom.
Okay. Look more towards the middle. Anybody see it? No? Okay. So.
Is it 188?
Yes. Okay. So watch 188. Now I'm going to put on my right turn signal. And so now we see 2. And if I do left, we see the data is representing 1. And then if I try to trigger them both at once, it's kind of hard to do that sometimes. Now we're seeing, yeah, it's iterating. It's going back and forth between 0 and 1, or 0 and 3, sorry. Or 1 and 3. Can't talk. So anyway, on a real car, there'd be a lot more going on. It might be hard to pick out something like this. So we're going to talk about a foolproof technique to essentially perform an action on a car and figure out exactly what frame controls that component of the car. But this is a nice visual way to do it in our safe little testing environment. Okay. So that is IC Sim and using CAN utils and virtual CAN devices. So let's move on to talking about, so yeah, CAN dump, it's fast. We see a lot of stuff going over the wire. Even if your car's in park, even if it's it's cycled off, but it's, like the engine's not running, there's still gonna be a lot of stuff going on to the wire. And this doesn't really help us understand what's going on because it's all in, it's all binary and we don't have any, English text that's telling us, like HTTP, what's going on. So I've showed CAN sniffer and how that's helpful. So anyway, you might be interested, and William, you kind of touched on this, but in terms of not a lot of documentation on what's going on the CAN bus, and you're absolutely right, that's usually proprietary information, and it can be separate for not only the car manufacturer, but even the model and even year to year. All that can be different, which makes it a pain. There are some manufacturers that will sell that for more commercial vehicles, but even then it's very expensive to get your hands on. So we can use a technique to reverse engineer the data fields and the arbitration IDs and understand what CAN frames are doing what on our car. Okay, so, oh man, I screwed it up. All right, you're getting everything at once. So we have what I like to call the binary search tactic, and what this involves is, so you begin logging, which there's, I believe it's CAN logger, CAN log, something like that. You begin logging or recording, basically kind of like a packet capture of all the device, or the frames that are going on the CAN bus. You perform whatever action that you're looking to reverse engineer or figure out like what frame is responsible for that. Let's say we're unlocking a door, and then you stop logging as soon as you can after that. Now you've got a log with a ton of frames because you've got a bunch of stuff going on the network, and you need to determine which one of those lines is responsible for performing said action. So now you perform essentially binary search on this, where you cut the log in half and you replay it onto the CAN frame using, or onto the CAN bus using CAN utils, because there's a CAN replayer, I believe it's called, to do that very easily. And then you cut that in half, you see, did the first half do it? If not, play the second half. Did the second half do it? Like unlock the door? Yes, it did. So then you throw away the half that didn't do it, you cut it in half again, and you repeat that process until you're down to one frame. And that frame is the arbitration ID and the exact data that's responsible for performing this action. And we'll see later, I do that on an actual car to lock the door. So does this technique or this process make sense to everyone? Okay, cool. Okay, so now getting into kind of real cars and how we can do this on an actual vehicle. There are many ways you can go about doing this. Some are better than others. I'm not saying my way was right, but this is the way I did it. So I had a Pi 3 sitting around. I think it was like 3B+, doesn't really matter. But there is a interface that a third-party company makes called the PiCan 2 that you can get for relatively cheap, and then you just attach it using the pins or the pinout provided on the Raspberry Pi, and then it provides basically a serial plug-in for an OBD2 cable, so you also need to purchase that. And then this is your OBD2, I believe it's 16-pin plug that gets plugged into the car. And then this gets, the serial part of the cable gets plugged into the Pi. And then there's a chip on board that essentially allows you to take data from the OBD2 port and then treat it as a networking device. Just like we did with the virtual CAN, well, now we've got an actual CAN device. Okay, so on the right here is kind of my setup. I was down in Louisiana visiting my parents, so I, of course, asked them if I could hack their car. They weren't happy about that at all, but I did it anyway. So it's a pretty simple setup. I'm not saying you have to do it this way, but this is the way I did it. I had my Pi here. Here you can see the cable going back to the OBD2 port, which, by the way, is usually under the the driver's side dash on the left side as you open the door. So you have to sometimes look underneath, basically where the steering wheel is located, and you'll see the port. It shouldn't be that hard to find. And then, so I'm plugging in there. I've got my Pi here. I've got a little 5-port switch. One cord's going into, Ethernet cord's going into my Pi, and the other into my laptop. I have Wi-Fi connected to the house for research to do on the internet. And then I've got a nice power cable running out here to power all my fun activities. Here's a really short video that I just sent over Snapchat. I don't know why I didn't take more video of this, yeah, so sorry about that. But anyway, here's a quick video. Here you can see I've got CAN utils loaded. It just blurred when it moved. But anyway, we've got a single CAN frame that we're playing back onto the CAN bus. And so using CAN send, and then you can hear the doors lock, and also on the Ford Edge, which was the car I was testing on, it also does the horn when it locks. So yeah, you can see the actual CAN frame is pretty simple. The arbitration ID 332 identifies, I have a spreadsheet of exactly what it does, but it's basically locking doors. And then this is the data piece that is to lock the driver's side door. And so that's essentially how that works. Okay, so yeah, you can do stuff without touching the button, but how is that? You know, that's cool to an extent, but not really. You know, we're not taking control of the car or anything like that. So what I'm doing here is just testing the safe stuff. I obviously don't want to do anything to my parents' car and really piss them off. But you can potentially, and it's been proven before, but via the CAN bus, you can bleed brakes, preventing a driver from using their brakes. On tractors or agronomy equipment, they usually have the TPMS sensors. When they're underinflated, the vehicle will actually reinflate the tires itself. So we can send information wirelessly that says, hey, the tires are underinflated. They need to be inflated when they're not really, and we can blow those tires up. We can turn on warning lights, compelling like a driver to pull to the side of the road, or a malicious actor could, and then who knows what. And then we talked about the autonomous control, like park assist. I think I go on to, yeah, autonomous, park assist, any sort of lane keep feature, or like active cruise control with radar or cameras or anything like that will enable the attacker to use that hardware that controls steering, that controls braking and accelerating from the CAN bus. Okay, so now I want to move away from CAN and talk about brute forcing keyless entry. Who has seen this on a car door before? Okay, so a lot of people. Yeah, so this is very common. When I was first going through calculating the probability and the time it would take to break into this, I was thinking, well, you have options 0 to 9, so you have 10 possibilities. Clearly, it's 10 to the 5th input possibilities, but upon further thought, that's actually not true. So on the cars, or at least on my Fusion, there are 5 digits in a passcode. However, the buttons are grouped together, 1 and 2, 3 and 4, 5, 6, 7, 8, and 9, 0. So you really only have 5 groups of possible inputs. So therefore, it's not 10 to the 5th, it's only 5 to the 5th. Yeah?
Wait, so there's no like push left side for this button, push right side for this button?
Not on my Fusion, which is a 2013. So it's.
You know, I've been lied to my entire life.
Yeah, so, yep. Yeah, there's no, at least not on my car, there's no like left and right. I don't know if anyone has anything. Yeah, okay, so same thing. Yeah, so you're grouping these into 5, which is greatly reducing the number of possibilities for a passcode, which as a potential malicious hacker is good for that person. So anyway, my car has rate limiting. On 7 failed attempts or inputs of a passcode, the car will disable the unlock feature for 60 seconds. So I want to know, how long is this going to take for me to brute force a code and get into someone's car to steal their nice MacBook on the passenger seat or something like that. Okay, so I'm in stats right now, so I'm using a little terminology from that. But anyway, the sample space is 5 to the 5 possibilities, which comes out to be just over 3,000 possible passcodes. And in case you don't know, understand the math behind that, we have 5 positions for a passcode, and then there's 5 possibilities for that position, being those 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 groups. So therefore, it is 5 to the 5th. So I estimated it would take us 2 seconds to enter each password, and each rate limit obviously costs us 60 seconds. And so we're looking at 74 seconds per group of 7 attempts. If we calculate how many groups we have, we come out to 447. And then if we multiply that by 74, we get 33,000 seconds, which comes out to 9 hours. That's a bit ridiculous. Nobody has time for that. If we go no rate limiting, it still doesn't help us much. We get it down to 1 hour and 45 minutes if your car doesn't have rate limiting. I don't know if any don't. It's potential. Wacker, do you know if the car you had?
I haven't tried it.
Yeah. When mine gets like wet and rain and stuff, and I try doing it, it'll like input it like a ton and then rate limit itself, which is pretty annoying. But anyway, there is a little trick out there. So the way the cars work, most of them anyway, is it is essentially like a first in, first out queue. So like, let's say I'm inputting like 1, 3, 5, 5, 5, and that's a potential code. So the car does not know whether, if we started with 1, it doesn't know if this is the first the passcode or input to the passcode. It doesn't know if this is the first. It doesn't know if this is the first, and so on. So this is essentially you're rolling your code. So the car is constantly checking your inputs, and we can keep going on. I can't write. We can keep going on, and it's going to say, okay, so 5 digits for the password, or for the passcode, 1, 2, 3, 4, 5. So this could be it. Or the car is going to check for this to be it. Or the car is going to check for this to be it. And it's going to keep going on. So we can take advantage of that. We don't have to input a passcode. The car tells us it's wrong and then input another one. We can take advantage of this rolling code feature or bug, if you will. I don't know. I would say it's more of a feature with the way vehicles work. But if we take into account that there's no rate limiting on this car, we can use a sequence that's been created and provided online that will get us into this car within 20 minutes or less. So I'll just open this up real quick. Hopefully it loads. Yes, so it's kind of hard to see, but you could easily print this out onto a few pieces of paper and have maybe someone read them to you, or just kind of look at it and input as you go. It looks like a lot, and I think it says it somewhere exactly how many entries this would be, but they've tested it and you can get it in about 20 minutes or less. Okay.
So if you're in the middle of a sequence of those and then the car rate limits you, do you have to start back at the beginning? Where do you start? Does it reset the rolling code when it rate limits?
So that's actually a very good question. I would want to say it's going to reset you, yes. So you would have to take that into account and kind of work through the math behind that, or like understanding from an entry perspective how that would work. So that's a very good point and something to consider for sure. Well, hopefully we're not all going out and trying this on people's cars, but yeah. So that would be something to take into consideration. Where did I? Okay. Okay, so now I want to talk about the tire pressure monitoring systems or sensors, or the TPMS. Man, none of these animations worked. Okay, my fault, but anyway. So in 2000, there was an act that was put in place by the government that required all vehicles to have this system or these sensors installed. And so on cars, there is a sensor in each tire. And so basically, if you've ever had a warning light come on that says your pressure's low or anything like that, chances are it was the sensor inside your car being able to tell that. I know, Arden, we were talking yesterday, and there are some older vehicles that will do this without a sensor, it does it more in a manual way with how the actual wheel is spinning and the rotational forces on that. But I don't know exactly how that works. But nowadays, most of the cars are using these sensors. So these sensors transmit wirelessly into the wheel well things like the tire pressure readings, the rotation of the wheel, any sort of warnings, and then the temperature where the sensor's at. And they actually transmit on 2 specific frequencies, which from a hacking perspective is good because we can then filter out on these frequencies to do reverse engineering or understand how this information is being wirelessly transmitted. Now, the interesting thing, and I've linked a talk at the end of this video, was they did a study, and the TPMS sensors can actually uniquely identify a car. And so at low speeds, this would allow for a malicious actor to track the vehicles coming through a specific area, such as a slow street like 25 miles per hour street, or into a parking garage or anything like that. And again, we talked about the agronomy vehicles reinflating their tires on their own, an attacker potentially telling the tires that they need to be inflated and blowing them up, which is extremely costly from a farming perspective, and as those tires are usually much larger, well, even car tires are just expensive. So, okay, and I believe this is kind of nearing the end of my talk, but I wanted to touch on infotainment systems. These are the devices in your center console. Some cars have more expansive ones in terms of features than others do, but they run typical operating systems that you've seen before, like Windows and Android and Linux, and also QNX and Green Hills, which are real-time operating systems. I don't know if they're as common as the other ones on there, but they have been found in infotainment systems. And so the attack vectors that we see from these IVIs are via USB, so you can update firmware. I have linked a book that talks about crafting malicious firmware updates and getting access, and the Jeep hackers did such a thing. I don't know if it was via USB, but messing with the firmware. And then also, you've got your CD input, and then also Bluetooth connectivity with your phone. I know Ford is pushing out, I forget the exact name of it, but they're pushing out a program that allows developers some sort of access to the IVI to develop applications that interface with phones. So they're giving us little by little more access to our car and connectivity. And so in terms of future research that I want to do with this area is definitely looking at the firmware and attack potentials for IVIs, but I ran out of time during my research for this talk. So that's all of my talk. I will put these slides out in IASG Slack, but these are all really good resources. One thing I do want to point out that was very helpful for me was the Car Hacker's Handbook. I bought it in print just because I like reading books in print, but you can get it for free online through No Starch Press, which is awesome. And then I've linked to all the materials from the Jeep hackers, which is really good stuff. They've got white papers and videos that you can look at. And then I linked some of the stuff I've talked about. One of the things I didn't hit on is a tool called Kayak, which is a GUI for dealing with the CAN bus, so you might want to check that out. And then I've got some notes that are going up on my website. I've got some stuff up on there now, but not a lot, and I'm writing stuff right now to publish, including step-by-step guides in terms of working with the vehicle, and then also IC-SIM and more. And then this is a talk I was discussing with the TPMS sensor, so check that out if that is at all interesting to you. And I've got my sources here for all the pictures and stuff, and that's pretty much it. So, any questions? No? Okay, thank you. Yeah, that's it.